3010 Climate Variability and Predictability session part 1. My name is Hai Lin, and today we have 5 presentations. Okay, and also I would like to take this opportunity to acknowledge the indigenous people of all the lands that we are on today. We do this to reaffirm our commitment and the responsibility in improving relationships between nations and to improving our own understanding of local indigenous peoples and their cultures. So by doing that, I think we can start the presentation. And the first one is by Professor Paul Kushner. He will talk about extending multi-parameter pattern scaling to interpret polar amplification in Earth system models. Paul, yours. Go ahead.
Thank you very much, Dr. Lin, and I appreciate the chance to share this work with you. It's work done in collaboration with Luke Fraser-Leach, who's a student here in Toronto, Stephanie Hay and Alexandre Odette, former students in our program who are now at Exeter and UCSC, respectively. This is a screenshot of a program we're running next year at the Kavli Institute for Theoretical Physics. I give the URL down there and invite you to take a look. It's called Polar 25, Physics of Changing Polar Climates. So the story today is it's starting in the middle of something. So there's a history now, I would say about roughly 10 years of work on exploring how coupled ocean atmosphere models respond to changes in sea ice in isolation from other aspects of global warming. Now, I have these figures here to motivate this approach. So this is a kind of standard format figure that's seen in a lot of assessments of climate change. It is the zonal mean cross-section as a function of latitude and pressure of the temperature response to greenhouse forcing or greenhouse-dominated forcing. This is actually external radiative forcing in a weaker scenario and a stronger scenario. We see a characteristic pattern of response with tropical upper tropospheric warming, polar amplification, and stratospheric cooling. And so what we want to understand better is the dynamics of polar amplification. There's a lot of interest in the causes and consequences of polar amplification. And one means to do this, it's not the only way, but one way to do this is to take a coupled ocean atmosphere model of the kind that's present in these left panels here, and isolate just the effect of reducing sea ice as a way of triggering polar amplification. Now, one clue I have to say is that in this slide here, the North Pole is on the left. This is a review paper in which several of these coupled ocean atmosphere sea ice experiments are done. So here, only sea ice has changed, nothing else, and we can go into the details. They don't really matter. The point is that sea ice loss in isolation triggers a certain amount of polar amplification, like we see in the full coupled runs of greenhouse forcing. And they also tend to excite teleconnected signals through the ocean and through the adjustment of the upper and dynamical ocean so that the signals from sea ice loss extend into the tropics and also, not shown here, but also into the southern hemisphere. So this has been known for some time. This is a paper from 2018. Features simulations that have been done in several groups, including here at Toronto. But recently, there's been a critique of these techniques, and it comes from Mark England and others, and includes some of the same investigators who were involved in the original simulations. And what Mark pointed out was that if you take a very simple energy balance model and look at the top of atmosphere energy balance, you can kind of predict what the actual effect of sea ice is. And as sea ice is lost, the main effect that you can understand in a very simple model is just a planetary albedo effect. And they call this the true sea ice effect. And this here represents the change in surface temperature in response to the sea ice effect, which is a moderate warming of about 2 or so degrees in the kind of particular cases that they were looking at. This black curve here represents the response to CO2 in this simple energy balance model. These red and blue curves represent a couple of sea ice loss experiments in which sea ice loss is imposed separate from greenhouse warming. And what they suggest is that because we're adding a lot of heat to melt the sea ice and maintain a sea ice in a perturbed state, that's actually inducing a lot of Arctic warming. And so, and that's shown here, the difference between then these sea ice loss experiments and the true sea ice effect is this purple arrow here, and that's the artificial Arctic amplification. So that's an important point. And we had to study this a while, but we were able to reproduce it and look at it in some detail. What we also learn is that as you do more of this kind of work, that the responses to sea ice really do depend on the model and on the method. That's one of the reasons we use many models to study it. So what we've been trying to do is use post-processing to understand better what's going on in these simulations. And we realize that there's some advantage to be gained by combining free-running greenhouse forced experiments like shown on the left and these sea ice loss experiments, and using an idea of pattern scaling to interpret them. Multi-parameter pattern scaling is an extension of standard pattern scaling based on levels of warming to include other variables. So what I'm going to do in this talk is extend multi-parameter pattern scaling to deal with artificial Arctic amplification and reinterpret some of the effects we've seen before. So after that rather long introduction, let me just jump to talk about multi-parameter pattern scaling. So the idea of multi-parameter pattern scaling is that you can diagnose the pattern of response to a given number of forcings, like greenhouse forcing or sea ice forcing in isolation. And we get these patterns, which are denoted delta Z, and the M is an index for the models. And then we can diagnose the response of N scaling parameters. And the scaling parameters can be global mean temperature, they could be sea ice extent, they could be tropical temperatures. There's some freedom to choose what they are. And then what we do is we use all this information from the models and the scaling parameters to infer what the change in a given quantity, Z could represent geopotential height or temperature, and S is like a sea ice indicator. And the partial derivatives here indicate that we are imagining holding other parameters fixed while this one parameter is changed. So this is a diagnostic technique. It's based on post-processing. It's a very simple mathematical operation where we just invert a 2x2 matrix for each sort of simulation set. And from that, we get these sensitivities. To show you this in action, this is from an older paper from Russell Blackport's thesis work. We were comparing the response to greenhouse forcing in a large ensemble of calculations to albedo-forced sea ice loss experiments where we change the albedo of the sea ice and we see Arctic warming and some tropical warming as well. And so what we do is we recombine these top two experiments to estimate or infer the partial response to the climate system to low latitude warming in the absence of sea ice loss. That's shown here in C. And to the converse or the complement is the response of the zonal mean temperature to sea ice loss in the absence of tropical warming. And you see here this very clean separation, okay? And this is set up so that D plus C is equal to A, so that we call these the partial responses. This is in temperature. When we do this to the zonal winds, what we see in these experiments is that when we look at the greenhouse forcing response to CO2 increases, there's very little change in the zonal mean zonal winds in this particular set of simulations. And this is kind of common. But when we impose sea ice loss by changing albedo, we see a pretty strong equatorward intensification of the winds. And our decomposition using the same scaling parameters as before shows a strong tug of war that to low latitude warming, we infer a strong poleward shift of the jet, and to sea ice loss, we infer a strong equatorward shift of the jet. So this scaling really suggests that there's a strong tug of war. So that's fine, but there is an issue here, and that is we're not really sure if the tug of war is a realistic effect, especially given that this true sea ice effect might be much less than the actual sea ice effect that comes out of these experiments. So what we've done is looked at alternate scalings. And we're motivated by working with this moist energy balance model. And results are shown here in the top two panels. Okay, the black is the total response. The blue and gold solid lines are the response to sea ice loss and low latitude warming using pattern scaling, multi-parameter pattern scaling. And the dashed lines here show a kind of a similar pattern of response, but using another type of scaling, which is based on the forcing response. Because what we're motivated here because we have a way of estimating how the forcing changes in these experiments. From the energy balance model, we realize that there's a way of estimating the shortwave top of atmosphere response. And if we use that response instead of the sea ice extent as a scaling parameter, we can actually get a different kind of estimate of the different effects. And this is really shown strongly here when we take an albedo forcing model simulation called dark ice for this moist EBM. And we see this strong tug of war in the change in temperature here. And that tug of war in the solid is really changed when we use a different scaling based on forcing. So what we're seeing when we use this alternate scaling, multi-parameter pattern scaling, is that the responses in the dark ice simulation and in this low albedo simulation from the community Earth system model of NCAR, they show a similar pattern. There's less of a tug of war. And in fact, we find that tropical warming is associated with polar amplification in addition to sea ice loss being, in addition to the sea ice response being associated with polar amplification. And we have good reasons to think that tropical warming is associated with some polar amplification just because of a simple polar moisture transport effect and diffusion of moist static energy. So what we're finding here is that this new way of this new scaling gives us a good interpretation. So in the last minute or so, because I think I'm not sure where my time is, but in the last minute or so, I'd just like to show you some results from a different kind of scaling based both on the forcing and also the idea that we can use lapse rate to estimate at low latitudes the change in lapse rate, giving kind of one scaling, and then we can use a separate scaling for high latitude lapse rate changes. And this is motivated by some feedback work from Feldwell et al. So rather than go too much into the motivation, I'm just going to sort of show you some results from this other alternate scaling that we've employed. So what I'm showing you here are some experiments from CESM again using albedo as a forcing. This is a doubled CO2 experiment and then an Arctic sea ice albedo change. And the sea ice extent scaling that I've emphasized a couple of times here is shown in the top row. The middle row shows sea ice forcing scaling using the top of atmosphere Arctic shortwave response as a scaling parameter instead of sea ice extent. And then the bottom row shows this lapse rate scaling where we use tropical lapse rate and lower atmospheric or lower tropospheric Arctic lapse rate as two scaling parameters. So these are scaling parameters based on the stratification in the Arctic and the tropics. And this gives us a kind of similar pattern of response, or similar breakdown of responses to the sea ice forcing scaling. But this scaling is much simpler because it's just based on lapse rate instead of estimates of the forcing. And when we apply that same method to another set of experiments, or system model experiments, these ones we're actually using forcing a nudging kind of effect to affect sea ice. We basically get the same kind of similarity between this hard to calculate sea ice forcing scaling and this relatively simple lapse rate scaling. So just to conclude, what we're trying to do here is choose scaling parameters that help us interpret these expensive and what I argue are really important experiments. Sea ice extent scaling is simple, but it really exaggerates this tug of war effect. And we think that we should move beyond sea ice extent scaling. Sea ice forcing scaling is more physically motivated and is linked more to the energetics, but it's actually hard to define objectively, and it's really dependent on forcing method. This lapse rate scaling is an alternative that's simple. It's closely linked to model sensitivities to feedbacks, and it gives a similar result to sea ice forcing scaling, at least for the cases we've analyzed. So we've been using this in a couple of settings, and so our next step is to really better justify these approaches, and especially to be able to relate these lapse rate scalings to the character of the feedbacks. And with that, I'll leave it. Thank you. Sorry, I went over a little bit.
Thank you, Paul. If you have any questions, please type it in the Q&A section, and I will read it out. So I can remind you for the next few presentations, you can type the questions at the same time you're listening to the presentations. So, Paul, I have one question. Probably myself is you mentioned the tagout wall, and that's the zonal average. Do you have similar things for the distribution of this response?
Yeah, I was trying to show you the simplest diagnostics, but we've used these methods to understand surface temperature distribution responses, ocean responses. So we look at all sorts of fields, the vertical structure and so on. So this is detailed in several papers now. What we're always trying to do is better justify using this post-processing technique. And we're not the only ones to do this kind of post-processing. We're just looking for the best method at this point.
Thank you. So, are there other questions? All right. So probably when it comes, you can answer it by the Q&A session. How about that? All right. Okay, so if there's no questions here, we can move to the next presentation by Wang. He will talk about diagnosing observed extratropical stationary wave changes in the boreal winter. Lei, go ahead, share your screen.
Thank you. Thank you. Hi. This is work done by my graduate student Wang, who is civil servant now. So, this topic has been started like almost 15 years ago when I was a graduate student with Paul. I like to share some of the recent results that it has been past almost 15 years, and now we have more data. This work has been published last year, and I hope I can explain a little bit in details here. The observed boreal winter surface temperature trend show kind of a large zonal asymmetry because of the normally we think about the zonal mean response, but if we look at the weather maps, we can see that there is a strong wave one structure in the surface temperature response. And similarly, we must have something similar in the general circulation to match with this temperature response. So if we look into the literatures about the changes in stationary wave under global warming, under different scenarios or different, for example, the Arctic amplification and this kind of topics, we can see some kind of general conclusion that they mostly support that the winter stationary wave will increase in amplitude in general will remain stable. And also we can see some eastward shift from models from CMOS 6, CMOS 5 or CMOS 3 models. And also we can see some kind of decreases in wave number. If we look into this different kind of studies, we can see that there are some kind of general agreement, but there are also very large spread due to different assumptions in the projections. So, so I think why don't we look at the observed stationary wave in the past several decades to say there was something we can learn from the observations. So a little bit about the background. If you attended the public lecture yesterday, Ruby Liang has nicely introduced the stationary waves and its and their impacts on the climate change. So now, if we look more into the details, the stationary wave is response is a function of the changes in zonal mean as well as zonal asymmetric forcings like diabatic heatings. topography, transients, and station nonlinearity, among which diabatic heating and topography is most important. However, if we break down them into different terms, we need to consider about the nonlinear interaction between them. So we use a nonlinear station wave model to automatically account for that, and then we ask questions about how have station waves changed in the past decades in the boreal winter, and which factors dominate the station wave changes in the past few decades. And can our state-of-the-art models like CMAP6 historical simulations capture these observed changes? So we use ERA5 as our reference observations, and we also use CMAP6 historical simulations to compare with. And we divide the past 6 decades into 3 periods and 20 years for each. And we use the same model as in Wang and Kushner 2011. So we set up the model with different zone low mean basic state, including UVT and zone low asymmetric diabatic heating from different periods, and the different combinations gave us a different response to either zone low mean or diabatic heating forcing, or both of them. In particular, we also look into some focus areas. So first, take a look at the station wave response in stream function at 250 hectopascal. We see that there is a strong wave 1 and wave 3 structure if we look into the details. And we found that the compare the station wave amplitude in the 3 periods, we found a significant increase in the wave amplitude, mostly in the middle latitudes. And if we decompose that, we can see there is an increase in wave number 1 in particular. And also, if we look into the stream function response in the stratosphere, we can see a larger scale wave 1 pattern again, and this is mostly at 60 north. So from the observations, we can see these, and we can see if we decompose them into the response to changes in zone low mean, we show here the zone low mean velocity and zone low velocity and the temperature pattern here, and also in the changes in zone low asymmetric diabatic heating. Now, if we look into the decomposition and also the combined response to the changes in zone low mean and the diabatic heating, we see a very similar pattern to the observations, and mostly from the changes in zone low mean in the troposphere, but a larger response in the stratosphere to the changes in zone low asymmetric heating. So if we further look into whether the CMAP6 models can reproduce them, the answer is unfortunately no. If we look at the 51 models, and only 3 of them kind of simulated the observed response in both troposphere and stratosphere. So if we calculate the model ensemble mean response relative to their standard errors, we found that the in the troposphere, the ensemble mean shows a decrease in wave amplitude, and with a much larger standard error, which means this is the tropospheric response is probably mostly internally due to internal atmospheric variability. And however, the stratospheric response show a large increase in amplitude, which is almost 2 to 3 times of their standard error. And they show that, which means that most of the models agree that there is an increase in wave amplitudes in the stratosphere. If we break down this into some kind of summary that we show there is a changes in zonal mean, and both in zonal mean and the zonally asymmetric forcings. The tropospherical response to mostly to the change in zonal mean, however, which it cannot be kind of attributed to the climate change. And the stratospheric response is a wave one pattern that mostly forced by changes in diabatic heating, and in particular, we look into the detail that diabatic heating in North Pacific and the Western Eurasia are important in drive this observed changes. Thank you for your attention.
Thank you, Lee. Okay, any questions and comment? Please use the Q&A to type it.
I dropped a question in the Q&A, but I guess I could ask it verbally.
Oh yes, please go ahead.
Hi, Lei. Can't believe it's been like 15 years.
Right.
Anyway, but I was just wondering if this is probably an answer is no, but is there anything interesting happening for like wave number 5 for some of the higher wave numbers? Because there's this ongoing interest in, the wave 5 kind of structure associated with the waveguide, the tropospheric waveguide, and evidence that extremes are kind of correlated in a sort of teleconnected wave 5 structure. I don't know if the wave structure is evident in these simulations, but have you looked at that?
Yes, we look at that for the winter station wave response. Mainly wave 1, 2, 3 is obvious. But if we look into the summer station wave response, we can see a wave 5 or even higher number response.
Right. Yeah.
And that's more evident in the meridional velocity rather than the stream function. I think the stream function tends to show larger wave number responses.
Yeah, interesting. And yeah, you made it clear that this was about boreal winter, but yeah, so it's good that you're seeing that. Yeah. Right. Is the stationary wave model capable of helping you interpret that?
You mean the summertime? Not yet. So we are still. I've asked another student to work on that, and it's still work in progress.
Good. All right. Keep me posted.
Thank you. Sure.
Thank you very much.
May I ask one question?
Yeah, of course. Go ahead.
Yeah. It's a very nice talk. I think here you try to separate the flow into stationary and eddy waves. Do you have any idea that whether the wave statistics you discuss here are sensitive to the resolution of the data you use?
Because we use mostly the diabatic heating as a zonal asymmetric force, and we didn't really use the transients as a forcing. So we didn't look into that. However, since most of the response can be reproduced by zonal mean and diabatic heating changes, so we didn't think that the transients would be important in this case. However, if we look into more details, we need a lot of daily data from these models to really kind of attribute the whether it's resolution dependent or not. Sorry, we didn't look into that.
Yeah, I guess the spatial resolution also maybe a concern here as well. Yeah,
Right.
thank you.
So,
All right, thank you. Any other questions? Okay. Now we can move on to the next presentation by Wogu Zhong. He will talk about interannual variability of the wintertime Asian-Bering-North American teleconnection linked to Eurasian snow cover and the Maritime Continent sea surface temperature. Go ahead, Wogu.
Oh, okay. Thank you, Dr. Herling, for your kind introduction. My name is Wogu Zhong, and I'm currently a PhD candidate at Fudan University in China. My supervisor is Professor Zhiwei Wu. Today, I would like to introduce our work about the Asian-Bering-North American teleconnection, and we call it the ABNA. Well, the ABNA teleconnection was first put forward by Dr. Yu in 2016. We all know that North American winter temperature anomalies are significantly related to the PNA. Dr. Yu's work suggested that after removing the impacts of the PNA, there exists a zonal wave chain in the mid-latitudes with 3 loading centers located in northern Asia, the Bering Sea and Strait, and eastern North America. That is the ABNA teleconnection. The ABNA is not only related to North American winter temperatures, but also to temperature anomalies in Asia. Therefore, the ABNA provides a paceway to connect in-phase temperature anomalies over these 2 continents. Well, further investigation suggested that the winter ABNA might be forced by snow cover anomalies over Siberia in the previous autumn. However, the underlying physical mechanisms are still unclear. Besides, it is widely recognized that the PNA pattern is associated with tropical ENSO events. Since the ABNA is independent of the PNA, this is guaranteed by the definition of the ABNA index. And now we wonder whether the ABNA is linked to other tropical forcings. Our study tries to explore these 2 issues. To deal with these 2 scientific questions, we first reconstruct the winter ABNA index following Dr. Yu's method. The key step is to remove the impacts of the PNA pattern on geopotential height anomalies through linear regression and get the residual geopotential height anomalies. Then we can calculate the ABNA index according to this equation. Here, the ABNA index is reversed as in Dr. Yu's work. We try to highlight its potential linkages with winter cold anomalies. We also use some common reanalysis datasets and statistical analysis methods to verify the physical mechanisms we proposed in this study. We also employed a linear parallel clinic model, LBM. Now let's look at the results. The winter ABNA index exhibits strong interannual variability with a slightly decreasing trend. The linear trend is not statistically significant. To focus on the interannual variability, we use the detrended index. The bottom 2 figures present a unique spatial pattern of the ABNA. There is a negative, positive, negative geopotential height anomaly pattern in the mid-latitudes. From the cross-section of geopotential height anomalies, we can see that the ABNA pattern it has an equivalent barotropic structure in the troposphere. These are the same as in previous work. We do find something different, that the ABNA is associated with stratospheric geopotential height anomalies over the Bering Sea and North America. This phenomenon implies that the ABNA is linked to changes in the Arctic stratospheric polar vortex. Well, the top right figure shows the correlation coefficient between the ABNA index and the winter surface air temperature anomalies. We can see that the ABNA is related to a distinct temperature anomaly pattern in the mid-latitudes. The left panel shows the correlation coefficient between winter surface air temperature anomalies and the PNA index, AO index, NAO index, and NPOD index. The right panel shows the partial correlation coefficient. That means if we controlled the impacts of these important teleconnections, the ABNA is still significantly correlated with surface air temperature anomalies in the mid-latitudes. These results suggest that the ABNA pattern is crucial for our understanding of winter temperature variability. Now we wonder about the origins and the physical mechanisms of the winter ABNA. As we have discussed, we will firstly evaluate the potential impacts of Eurasian snow cover. Well, this figure shows the regression map of November snow cover anomalies onto the ABNA index. We can see that the ABNA is positively correlated with snow cover anomalies in Northeastern Asia and negatively correlated with snow cover anomalies in Europe. This distinct dipole pattern is labeled as the ESCDP. Here we define the ESDP index as the difference of snow cover anomalies between Northeastern Asia and Europe. The right figure presents the regression maps of circulation anomalies onto the ESDP index. Well, we can see that according to the albedo effect, excessive snow cover over Northeastern Asia is accompanied by a cyclonic anomaly, while reduced snow cover over Europe is linked to an anticyclonic anomaly. In the meanwhile, we can see that a significant anticyclonic anomaly can be detected in the stratosphere and it's most pronounced over the Bering Sea in the Arctic regions. This means that this actually means that the Arctic stratosphere polar vortex is weakened and displaced. Well, from this figure, we can show the black contours shows the climatology of winter polar vortex, while the red contours show the impacts of the ESCDP. We can see that the ESCDP can lead to a weakened and displaced Arctic polar vortex. It exhibits a stretching structure to both to the Asian and the North American continents. Well, these are based on observations. We have also designed a LBM experiment by adding a cooling forcing over Northeastern Asia and heating forcing over Europe to simulate the thermal impact of snow cover changes. We can see that an anticyclonic anomaly is clearly detected over the Bering Sea. Therefore, the ESCDP can induce a weakening and displacement of the stratospheric polar vortex. We also diagnose the EP flux. The ESCDP is associated with upward EP flux in November. This will lead to a weakened and displaced polar vortex, and the anomalous polar vortex tends to persist into the winter months and propagate downward to the troposphere, therefore generating the tropospheric ABNA pattern. We can conclude that the coupling of the troposphere and the stratosphere is an important paceway in connecting the Eurasian snow cover changes and the winter ABNA pattern. Now let's take a look at the tropical region of the ABNA. This figure shows the regression maps of SST anomalies onto the ABNA index. Here we find that the ABNA is significantly correlated with a positive SST anomaly in the Maritime Continent in the previous November. That is, we call it the MCSST. However, the relationship between the ABNA and the MCSST gradually weakens in the winter months. We have further examined the precipitation anomalies associated with the MCSST. We can see that increased precipitation can be identified over the tropical Western Pacific TWPP plays an important role in prolonging the impact of the MCSST. Here we analyze the wave activity flux associated with the MCSST and also the TWPP. Well, latent heat released associated with tropical precipitation can generate poleward propagating low speed waves, and this wave chain propagates first northward from northwestern Pacific to northeastern Asia, and then turns to the Bering Sea, and finally flowing downstream to the North American continent. And this wave pattern resembles the ABNA teleconnection. Here, we also design a LBM experiment by adding heat enforcing over the tropical Western Pacific. Through the evolution of the atmospheric response, we can see that the low speed wave propagates poleward, and it can generate the ABNA pattern in the mid latitudes. This pattern is a little bit different from those in observations because here we use the winter climatology. If we change the basic state to a suitable situation, the ABNA pattern can be more pronounced. After revealing the influencing mechanisms of the Eurasian snow cover changes and the Maritime Continent SST, we try to access the contributions of these precursors to seasonal prediction of the ABNA. The top figure shows the cross-validated estimates of the handcast results. The empirical model based on these two predictors show a correlation of 0.7 with the ABNA index. This is pretty convincing. And if we use this model to predict winter SAT, we can see that a large portion of SAT variances can be reasonably predicted, and this can provide a useful tool for seasonal prediction of winter climate in the mid-latitudes. Okay, I will briefly summarize our work here. The winter ABNA is an important teleconnection pattern. The extratropical origin of the ABNA is Eurasian snow cover. The ESDDP, well, it can induce troposphere and stratosphere coupling processes and lead to a displacement of the stratospheric polar vortex. The tropical origin of the ABNA is the Maritime Continent SST. It could lead to a poleward propagating low speed wave chain and directly strengthens the ABNA. And these two precursors have important implications for seasonal prediction of winter climates. That's all. Thank you for your attention.
Thank you, Wogu. Any questions? Please use the Q&A.
May I ask one question?
Yeah, sure. Go ahead.
It's a very nice talk. Thank you so much. I learned from this presentation. I have one quick question. Are these two forcing factors, the snow cover and tropical heating, they are correlated or they acting independently?
Well, here we analyze the from the index, the Eurasian snow cover anomalies and the Maritime Continent SST, they are not significantly correlated, and they can be considered as independent predictors for the winter ABNA pattern.
Thank you.
Thank you.
Yeah, maybe myself, I have one question is, what is the relative importance of the snow cover contribution and the tropical contribution? Which one is more important?
Well, from our analysis, the snow cover changes are more important because if we use the here we use the snow cover changes to establish an empirical model. We can see that use only the snow cover changes to as the predictor to establish the model. The correlation coefficient can reach 0.68, and if we use Maritime Continent SST to predict the winter ABNA, it is only 0.46. So here we propose that extratropical forcings are more important for the winter ABNA. Thank you.
Thank you. So if you have further questions, I can still type in it in the Q&A section. Thank you. All right. Okay. Thank you, Wogu. And let's move on to the next presentation by Jeong. He will talk about unprecedented 2021 heat wave over Western North America, increasing intensity and the frequency of humidex and the temperature extremes in warming climate. Go ahead, David.
Okay, so thank you very much, Dr. Lee. So we investigated the 2021 heatwave event over the Western North America, particularly for the human perceived heat stress quantified by Humidex, and then the increasing intensity and frequency of the Humidex and temperature extremes in a warming climate over the Western North America region. So I want to thank to my co-authors, Binu and Alex Cannon, and also Kenneth Cho for his help in preparing the multimodal ensemble used in this study. Okay, so there was a record-breaking heat wave from late June to early July 2021 across Western North America, and many researchers showed that how the event was severe using the different index and the approach in terms of the climatological perspective and weather perspective too. The event resulted in a lot of severe impact, including the more than 1,400 deaths. And Jeong et al. Reported that without reducing emission below intermediate levels, then the areas Western North America will regularly face extreme summer temperatures like 2021. But the previous studies focused on temperature only, and human perceived heat stress resulted by the 2021 heatwave event over the region has been overlooked. But there are significant risks to human health associated with the combined impact of temperature and humidity as shown in the cartoon. So we investigated the human perceived heat stress quantified by Humidex, which is the operational index using in Canada, in the Western North America region during the 2021 heat wave. We investigated project changes in Humidex and temperature extremes with uncertainty due to GCM model structure and internal variability. And we also evaluated the likelihood of extreme Humidex and temperature event surpassing 2021 level across the Western North America. Okay, so we used ERA5 reanalysis dataset for historical assessment and 19 CMOS GCM under 3 different emission scenarios. And 3 of them have initial condition ensembles, which are ACC ESS ESM model and Kenny ESM5 and MPI ESM12 era. And I want to highlight in here that each model has different climate sensitivity to greenhouse gas pulsing. And you see there's the equilibrium climate sensitivity, and then Kenny ESM5 is one of the most sensitive models to the greenhouse gas pulsing. So we use daily maximum temperature, TX, daily minimum relative humidity, RHN, to quantify daily maximum humidex, HX. We used 2 different extreme indices for the extended summer from June to September, HX6 and TX6, which are maxima of 6-day mean values, considers the intensity and the 6-day consecutive days. And HX95 and TX95, they are 95th percentile, roughly corresponding to the 6th highest daily value during the extended summer period. So we picked the extreme indices to represent the 2021 event well, and the duration of the heat wave mostly more than 6 days at the western north part of America. Okay, so we applied the bias correction, quantile delta mapping before the projection. So you can see the blue symbols shows better performance in terms of the spatial pattern of mean and standard deviation of HX95 and TX95 when compared to the original value. And we presented the project changes to 3 global warming level relative to the pre-industrial era. And we used 2 ways of the presentation. One is the common way using the fixed 20-year period for all GCM. And then the period was from IPCC AR6 report. And 20-year periods associated with each global warming level calculated separately from the individual GCMs. So why are we doing this? To communicate the project changes without incorporating the uncertainty associated with the differing climate sensitivity of GCMs to external pulsing. They are showing the daily anomaly of TX, HX, and RHN during the 2021 heat wave. And you can see that the high positive value of daily maximum temperatures. And we selected the contoured areas as a study area of these studies, Western North America. But simultaneously, you can see the below normal relative humidity at that time and at the same areas, which means that the heat wave occurred at the drier condition based on the situated atmospheric blocking and high pressure system and at that period. But simultaneously, you can see there's the above normal Humidex index at the same area and same days, which is mainly driven by the record-breaking air temperatures, even if it was a drier condition. Okay, so when you see there's the relationship in between air temperatures and relative humidity and Humidex, Humidex has a non-linear monotonic increasing relationship with air temperatures. So if the air temperature is 30, then the Humidex changes from 28 to 45 degrees C at the given number of relative humidity from 20 to 90%. If we plot the HX6 with associated air temperature and relative humidity in that relationship, then you can see that the 2021 event was record-breaking, particularly driven by the record-breaking air temperatures in years. But the relative humidity is smaller than normals, but it is in the range of the record, which means some atmospheric moistures was provided from North Pacific to these areas through the atmospheric rivers in that heat wave event. Okay, so there are anomaly and increasing trend of the Humidex and temperature extreme indices, and you can see that the 2021 event show high positive anomaly when compared to the reference period from 1981 to 2010, 30-year period. And when you see the time series of the indices, then you can see some increasing trend at all indices. And I want to highlight that the HX6 and TX6 exhibited a higher positive anomaly when compared to the HX95 and TX95, which means that the when we consider the persistence of the heat wave event during the 2021, then it looks much more outliers when we only consider the magnitude. So you can see that Humidex extremes show higher rate of increase than temperature extremes when you see the trend line and the coefficient of the linear trend, which means that the nonlinear relationship in between Humidex and temperatures given the minor changes in the relative humidity. Okay, so this figure shows contemporaneous of the index between HX6 and TX6. So if the 100% value in here, then the HX6 and TX6 are perfectly overlapped during the 6 days. And you can see the higher value of contemporaneous at the northern part of North America is based on the large linear correlation in between HX and TX. But the contemporaneous decrease recent years because of the increased variability of relative humidity nowadays. But this tendency was not followed by the 2021 event because the HX6 and TX6 are mostly overlapped at the time. Okay, so they are project changes on the 3 different emission scenarios and the signal to noise ratios. So you can see the projected increase in Humidex extremes exceed those of temperature extremes when you see these 2 figures. And then a clear increasing signal is expected to emerge earlier for the HX6 than TX6, which means the signal to noise ratios is much more clear at the Humidex extremes than the temperature extreme. And we have the similar result from the HX95 and TX95. Okay, so they are project changes on of the multimodal ensembles on the high emission scenarios. We plot the individual GCM model projections in here, and you can see the KNESM5, the green line, show the projections largest than the other models. But after we controlling the climate sensitivity of GCM to greenhouse gas emission, the project changes across the different global warming levels show the smaller uncertainty range when we use the fixed 20-year period to all GCM models. They are project changes to the initial condition ensembles. So at each individual models, the range of initial condition ensembles are not that different in the 2 way of presentations, which means that the internal variability looks much more dominant when after we controlling the climate sensitivity of GCM in the projection. Okay. So they are project changes of the return period of the 2021 event levels using the Gumbel distributions, and we can say that as global mean temperature increase, then the return period will decrease in the futures for all extreme event, and at 4 degrees C global warming levels, these extremes will occur every almost annually over the Western North America regions. Okay, so in summary, we show that the 2021 heat wave over Western North America resulted in record-breaking human perceived heat stress too, and Humidex extreme shows faster and larger increase than air temperatures in the historical period and future period projection too. and controlling for difference of GCM climate sensitivity to greenhouse gas pulsing is robust projection, reducing the range of project changes from the multimodal ensembles, and it looks much more dominant of the initial condition ensembles, mean the internal variability in that way projection. Okay, so thank you very much for your attention.
Thank you. So any questions, please use the Q&A to type your questions. So the temperature and the humidity, normally they are correlated. Higher temperature and can contain more moisture. So in that sense, they are not independent. So those kind of index that contain both parameters, how can we like differentiate this relative contribution of temperature and the humidity?
Okay, so when I show the contemporaneous between the humidex extreme and temperature extremes, it is not perfectly overlapped together, and the difference of the contemporaneous is much lower at the southern part of North America. That's because the relationship in between humidex and temperatures are much more variables at the higher temperature the condition compared to the lower temperature condition. So it's mostly occurs together, but there's some difference, and then the difference is highly relevant to the atmospheric moistures. I mean relative humidity in that the event.
All right, thank you. Okay, so let's move on to our next presentation by Bin Yu. He's talking about projected changes of the warm Arctic, cold North American pattern. Bin, go ahead.
Yeah, thank you, Hai. This is a study on projected future changes of the warm Arctic, cold North American pattern collaborated with Highland. We know that increases greenhouse gases lead to increase in global mean surface temperature. However, unexpected cold events in North America and also in Eurasia over the past 2 decades have raised questions about the connection between global warming and extreme cold events, and suggested the need to further understand Northern Hemisphere winter surface air temperature anomalies. So the warm Arctic cold continents pattern, or WACC, in short, it's one focus in this topic. This WACC pattern features Arctic warming together with cold winter in mid-latitudes Eurasia. So it's named the warm Arctic cold Eurasia, or WACE pattern, and cold in North America means the WCNA pattern. These patterns have been found in long-term trend and also in intraseasonal, interannual, and interdecadal variability of surface air temperature. The formation of the North American part, WCNA, has been attributed to both the external forcing and internal climate variability, such as anomalies in mid-high latitudes snow cover and sea ice, tropical convection and ENSO SST anomalies, and atmospheric circulation anomalies. The anthropogenic global warming features Arctic circulation anomaly, Arctic amplification, and tropical ENSO-like SST anomaly. So these are closely related to the formation of WCNA. So the question we ask here are, how's the WCNA pattern expected to change with global warming? Are these changes expected in its intensity and or spatial structure? And then what are the physical mechanisms driving the WCNA pattern in terms of the temperature variance budget? And how do these mechanisms change with global warming? We address these questions by using the EIA5 reanalysis data and also the Kang ESM5 large ensemble historical and high emission scenario simulations. Now let's look at the results. This slide here shows the WCNA pattern in EIA5 and Kang ESM5. The patterns shows a dipole structure with opposite centers over the Sukchi-Bering Sea or CBS in short, and also the Great Plains over North America. Kang ESM5 can reasonably well simulate these patterns, but with action centers are slightly stronger, and also it shifts slightly eastward. And then to examine the pattern changes, we project the surface air temperature anomalies over 30 winters, December, January, February, running window from 1951 to 2100 onto the simulated WCNA pattern over the North American sector, the green box here. And then the amplitude of WCNA variability is considered as the standard deviation of each project time series. And the ensemble mean WCNA amplitude indicated by the thick green curve here indicated decreasing with global warming, especially under the SSP foreseen after 2015. To further examine changes in spatial structure of WCNA, similar projection can be made over the two action centers, the CBS Center and North American Center. And then we can see the CBS variability, as indicated by the red curve here, shows a much faster decrease than the North American variability indicated by the blue curve here. We have also estimated the ensemble spread among the 50 members indicated by the thin lines here. The most changes have shows the signal to noise ratio values above 10, indicating very strong foreseen changes compared to internal variability. Changes in WCNA pattern intensity and spatial structure are also clear when comparing the patterns from the early 30 years over 1951 to 1980 to a later 30 period, 2071 to 2100. So we can see that the dipole structure appear in both periods, but it's clearly more asymmetric in a later period. And then the difference of these regression values indicated they have a negative values over CBS region, but positive values over North America, which indicated that the both center decrease in strength with global warming. However, the maximum temperature anomalies over the CBS drop from 2.8 degree to 1.3 degree. It's much bigger than the changes over North America, maximum center minus 0.38 to minus 3.1 degree. And the changes also show slightly westward shift with global warming. The decrease in both centers can be seen more clear when we compare difference of the regression squares, which indicated a change in the temperature variance associated with the WCNA pattern. And then to understand the generation and maintenance of WCNA, we examine the temperature variance budget. From the thermodynamic energy equation, we can get the temperature variance equation like this. We don't want to go to too detail of this equation, but as we'll see later, there are three dominant terms here. One is a VT1, which indicated the meridional heat transport along the temperature gradient, and the TS, which indicated the covariance between temperature and the effect related to vertical motion and to static stability. And TR indicated covariance between temperature and diabatic heating, which is considered as a residual. And then we can see the results. This slide here shows the WCNA associated temperature varying budget at 925 millibar in EIA5. We see that these are three dominant terms. So VT1 here try to support the WCNA pattern, and it's mainly damped by the TR, like temperature and diabatic heating covariance. And also TS contributed to this budget. The other terms have a relatively weak contribution, and similar result can be seen in Kang ESM5. So we further compare the three dominant terms between EIA5 and Kang ESM5. So we can see that VT1 is responsible for the increase of WCNA variability with high values over CBS and North American centers, corresponding to the two WCNA action centers. And these are mainly damped by the TR, covariance between temperature and diabatic heating. TS also contributed to the budget. It shows positive values along the Chukchi and central western Canada, but negative values over the Bering Sea and along the western coast of Canada. Similar feature can be seen in EIA5 and in Kang ESM5, except for the intensity difference. The VT1 and TR over the CBS center is about 20 to 30% stronger in Kang ESM5 compared to EIA5, which also correspond to the slightly stronger WCNA pattern center over CBS, as we saw above. We then look at the changes in WCNA associated temperature budget between the later period and early period using the model simulation. We see the changes still shows three dominant terms, VT1, TS, TR. The decreases with a decrease in meridianal heat transport supporting WCNA decrease. This decrease is stronger in CBS center than North America, which explain the larger WCNA amplitude decrease in CBS. And the changes in this VT1 term as mainly balanced by changes in TR and TS. Changes in VT1 is dominated by changes in the mean temperature term. This contribution is about 2 to 3 times bigger than compared to the other two terms, influenced by changes in heat flux and also changes by both the mean temperature and heat flux changes. So these dominant terms influence in the mean temperature indicated that these heat flux change is mainly related to Arctic amplification associated with global warming, as Arctic amplification will reduce the equator to polar temperature gradients, and then leading to a lower meridional heat transport. We also compare the time evolution of WCN-related budget change over the two dominant regions, Chukchi, CBS, and North America. And we can see that these changes are getting stronger with global warming. And the results again highlight the stronger budget changes in CBS compared to North America. And it also shows that these WCNA decrease is mainly due to decrease in the meridional heat transport and balanced by the covariance between temperature and diabatic heating. So to sum up, we found the WCNA variability decreases with global warming, with a faster decrease in Chukchi Bering Seas than North America. The WCNA variability is mainly generated by meridional heat transport and damped by the covariance between temperature and diabatic heating. WCNA change are driven by changes in meridional heat transport, which is related to Arctic amplification associated with global warming. I stop here. Thank you very much for your attention.
Thank you, Bin. If you have questions, please use the Q&A box to type your questions. Maybe, Bin, could you say a few words about the possibility of the model dependence of this warm Arctic North American pattern? You used one model, yeah.
Yeah. That's a good question. We actually discussed about this before, and because we know that the Kang ESM 5 has a pretty high climate sensitivity compared to most CMAP6 models. So I guess we can expect that the energy budget terms will be a bit higher, like a value. I mean, the amplitude will be higher compared to others. So it will be nice to look at the uncertainty of the budget and also the uncertainty of the WCNA variability itself change with global warming.
Thank you. Thank you very much.
Mm-hmm.
I have a question if there's time.
Yeah, sure. Yeah, Paul,
yeah,
go ahead.
Or kind of a suggestion and a question. So I think there's some older literature where people do this variance budget calculation, we found this too for some of our work, that it helps to look at the vector flux like v prime t prime, but the vector velocity covariance with temperature, and decompose it using a Helmholtz decomposition, which decomposes the flux into a rotational and a divergent term. And the reason that is because the rotational term has a lot of structure in it. So there's part of these fluxes, the U components have a lot of there's a lot of extra structure just because of the kinematics that are suggested here. Like in the vicinity of a temperature maximum, you get kind of the fluxes kind of have a strong rotational component. So if you remove that, then you get kind of the heat flux, the part of the flux that's going into convergence and divergence of heat flux, which might give you a better local picture. I'm just suggesting that because maybe some of the structure you're seeing is actually involving just redistribution of heat rather than like convergence of heat. I don't know, I can't say for sure, but it's not that hard. You can do a vector decomposition using like spherical harmonic decomposition, and there's some pretty standard packages. Maybe you've done this before, but I found it's been, for other contexts, it's been helpful to when you do this kind of local budget analysis.
Yeah, that's a good point. I think we actually have checked those for example, like here I put actually several,
pretty weak, yeah.
But we look at the individual contribution. Both of them are weak, and then to address your concern, that's why we look at the evolution.
Okay.
Evolution. We actually check the this kind of evolution, and we calculate every term in that equation, and it's quite stable changes.
Okay. All right. Yeah. No, I just have noticed it in other settings, so I just thought I'd mention it.
Yeah. Thank you.
Sure.
Thank you very much. So if there's no other questions, I think we can conclude this part of the session. I would like to thank all of the speakers for their presentation, and also I want to thank all of you for attending this session. As a reminder, we have a part 2 of this climate variability and predictability session starting at 2:05 East daytime in half an hour. Please come back. Thank you very much, everybody. Bye-bye.
Thank you.
Thank you. Thank you. Bye.
Thank you very much. Bye-bye.